Okay, so today we move into section 9.3 on uncountably infinite sets. So let me just recap. We have finite sets, and by definition, those are sets that you can put in bijection with the first k integers. So there exists some k. Let's say finite sets A. There exists a k such that A is equinumerous with n sub k. I guess I started at 0. Or equivalently, there exists a bijection A to n sub k. Then we had countably infinite sets. A. And to be countably infinite by definition was to be equinumerous with the natural numbers, right? So there exists a bijection A to n or n to A. And then we proved a lemma that said this is something like you can list all the elements of A. And then we said that these, if you're either finite or you're countably infinite, you say that these sets are countable. Because you can obviously count all of the elements in a finite set, but if you have a countably infinite set, you can like read off the elements one by one. It's like you can sort of count all of the elements somehow. And we have several examples of these countably infinite sets. So we know that n is equinumerous with z. It's also equinumerous with n cross n, even though that set seems bigger. It's also equinumerous with q. So what we don't yet have is we don't have any examples that we know of uncountably infinite sets. So you just say that something is uncountably infinite if it's infinite, but it's not countable, right? I guess I should also say that we said that the cardinality of n is the Hebrew letter aleph naught. That's like the smallest infinity, right? So this is also the cardinality of z. It's also the cardinality of q. But it seems kind of weird. Like, how can there possibly be a set that's so big I can't even list all of its elements? But these sets do exist, and we'll see like some very beautiful proofs today. So there will be infinite sets, we'll see, that are not in bijection with n. And since they're not in bijection with n, there's sort of no way to just list every element. If we ever tried to list all of the elements, our list would never be complete. So the question becomes where should we go looking for an uncountable set or an uncountably infinite set? So I would suggest maybe R or maybe the positive reals, right? We looked at the non-negative rationals last time. Maybe the complex numbers, or maybe even the interval from 0 to 1. We could ask, well, can you put these in bijection with n? Or even can you put them in bijection with one another? It turns out that these actually all have the same cardinality. We'll see. These all have cardinality, which are the same. And that cardinality I'll denote with a fancy C. It's a fraktur C. So I don't know. In LaTeX, you get math frac C. Fraktur, that's like the German style lettering. And this C will stand for continuum. So like the interval from 0 to 1, right? You can picture it like this. It's all the real numbers in here. And the point is that like when I shade in this interval, I really mean every single real number in this interval. This is like a continuous set. The integers are like a discrete set, or even the rationals are like a discrete set, which sort of means like you can put a dot for every integer. The point is that like I can never put a dot for every real number because there's even more real numbers in between every single dot, and somehow it fills up the entire line. Okay, so what we'll show in our first, the first thing that we're going to try to show is that this interval from 0 to 1 is an uncountable set. That's our goal. Show that 0, 1 is uncountable. Okay. So we need a key definition before we can try to understand real numbers. Here's the definition. A decimal representation of a real number A is in what we call normalized form if it does not end with an infinite string of zeros, of nines. Right, so if you did have, so first of all, like given any real number, there's many ways to talk about a real number, but maybe the one we're most familiar with is to write down its decimal representation. And the point is that if you did have a real number that ended in an infinite string of zeros, right, like if you had the real number 0.3699999, and I said, okay, well, every other digit is a 9, then we also know, I mean, hopefully, that this is just the same thing as the real number 0.37. These are the same real number. You can show that. And it turns out, so right, the point is, the problem here is that we can write the same real number in two different ways with two different decimal expansions. In two different ways. Right, those are different decimals because they disagree at every place other than tenths place. But it turns out that this is the only time when you can write the same real number in two different decimal representations. The only way to do it is if you either have an infinite string of nines, in which case you could like just choose the one that ended in an infinite string of zeros. Which means that if I assume that all my real numbers are in normalized form, then they are uniquely determined by their decimal representation. Every real number has a unique representation in normalized form. It's not true that every real number has a unique decimal representation because here's a real number with two different decimal representations, but this is the only time that it's not unique. So I'll just state this as a theorem. It's kind of technical to prove. But two decimal numbers in normalized form are equal if and only if they have identical digits in each decimal position. Okay, so sort of implicitly, you've believed this your entire life. I bet even like when you were younger, you thought that maybe these numbers were different because they have different decimal representations. But hopefully you've seen, and I think many of you have, if not, you should look it up. Hopefully you've seen a proof that 0.9 repeating is actually equal to 1. There's many, many proofs of this fact. And so you can use that, basically this result, to prove that these two are the same real number, even though they have different decimal representations. So it's not true that every real number, that a real number is determined by its decimal representation in some sense. Sorry. It's not true that every real number has a unique decimal representation, but it is true every other time except for this infinite string of nines. And so if we put them in normalized form, then it is true. You can tell if two real numbers are the same just by comparing their decimal representations. Okay. Now what we'll do, now we're ready. This is all the setup I needed. We'll prove that the interval from 0 to 1 is uncountable. And we'll do it using a technique called Cantor diagonalization. So now we prove 0, 1 is uncountable using Cantor diagonalization. It's a really clever, very beautiful technique. That's why it has the name. That's why it has a name. And as suggested by the name, this was invented by Cantor, who I've already talked about as the founder of modern set theory. So here's the theorem. You should always remember the theorem and always remember the proof. So it's just the open interval between 0 and 1 is uncountable. Okay, so here's the proof. So how do you show that a set is uncountable? Well, first you need to show that it's infinite, and then you need to show that it can't be in bijection. You can't put it in bijection with n. Okay, well, certainly the interval 0, 1 contains an infinite set. Say 1, 1/2, 1/3, 1/4, 1/5. Sorry, not 1, right? But 1/2, 1/3, 1/5, dot, dot, dot. And this you can put in bijection with n, so it's infinite. And we had a theorem from last time that if you contain an infinite set as a subset, you're definitely infinite. So by theorem from last time, this interval is infinite. Therefore, it's either countably infinite or it's uncountable. Those are the only two possibilities. So we'll show that it's not countably infinite by showing that there does not exist a bijection from n to 0, 1. Therefore, by definition, it's not countable. So we will show there does not exist a bijection f from n to 0, 1. Okay, so now let's suppose that we have any function. Let's suppose that I have any function. I have to show you that this function can never be bijective. In fact, if you think about this for a second, basically I'm claiming that the interval is way bigger than the natural numbers. So what will actually fail is it will actually never be surjective. That's the problem. Okay, there's definitely ways to get an injective function, but I'll show that f can never be surjective. Is not surjective, but that means it's not bijective, which means that 0, 1 is not countable. So for each natural number n, what I'll do is I'll write f of n in normalized form. Right, f of n is some real number between 0 and 1. So let's write it like this. So f of 0, it's a real number between 0 and 1. So it starts off with 0 point. And then let's write it like this: a sub 0, 0, a sub 0, 1, a sub 0, 2, a sub 0, 3, a sub 0, 4. It has some decimal representation like this, where each of these digits is a digit between 0 and 9. Right, then f of 1 is 0.a10, a11, a12, a13, a14. F of 2 is 0.a sub 20, a sub 21, a sub 22, a sub 23, a sub 24. F of 3 is 0.a sub 30, a sub 31, a sub 32, a sub 33, a sub 34. So what I'm doing is I'm just listing all of the f of n's as a sub n0, a sub n1, a sub n2, a sub n3, a sub n4, etc. Right? In other words, I mean a sub ij is the jth decimal place of f of I. And the trick behind Cantor diagonalization is I'm going to construct a real number that does not appear on my list. Okay, so we will construct a real number b, which will look like 0.b1, b2, b3, b4, that's in the interval 0, 1 in normalized form, which is not on our list. And I'll construct b one decimal place at a time. Okay, and the very clever idea here is I'll make b, sorry, I guess I should say, I should start at b0. I'm starting all my indexing at 0. 0.b0, b1, b2. The clever trick here is to make b0 different from a sub 0, 0. Then I'll make b1 different from a sub 1, 1. I'll make b2 different from a sub 2, 2. I'll make b3 different from a sub 3, 3. I'll go down this diagonal. This is why it's called Cantor diagonalization. And I'll make sure that my new number is different from the ith number in the ith decimal place. And then the number that I'll be left with, this b, will not appear anywhere on my list because it will differ in one of the decimal places. Okay, I do need to make sure that that the b that I construct is in normalized form. So I need to make sure that it doesn't end in an infinite string of 9s, because then it wouldn't be in normalized form, and then it might be on my list because maybe it differed in a place, but that's because it had an infinite string of 9s and the other number had 0s there. And I also need to make sure that this number b is not going to be 0, because that, I guess, could happen if you were just, okay, well, if this one wasn't 0, I'll choose b0 equals 0. If this one isn't 0, I'll choose b1 equals 0. But the point is that I have 10 digits to choose from, so I can easily make sure that b isn't 0 and that b does not end in an infinite string of 9s. So here's what I'll do. I will define b sub k to be 3 if a sub kk is not equal to 3, and I'll make it 4 if a sub kk is equal to 3. So what am I doing? I'm going down my list and saying, okay, well, is this first, the 0th digit of f of 0, is that 3 or is it not 3? If it's not 3, I'll just make my number 3. If it is 3, I'll make it 4. Regardless, I'll make it different, but also this will guarantee that b will not be 0 and will not end in an infinite string of 9s. In fact, its decimal representation will consist entirely of 3s or 4s. Right, so b is going to look like something like 0.334, 3333334, 34334, right? Something like this, because most of the time I'll end up picking 3. But if there happened to be a 3 somewhere, I'll choose a 4. So it's clear that, I mean, this is like an example of what b could look like. So it is clear that b is not equal to 0 because it has only 3s and 4s in its decimal expansion, and it is in normalized form. Right? It's in fact clear that b is in the interval from 0 to 1 because it starts with a 0 and then it's somewhere between 0.3 and 0.5, I guess. Right? In fact, 0.3 is less than b is less than 0.5. Further, for each n in n, b is not equal to f of n since they differ in the nth decimal place. At least, right? I chose b0 to be different from a sub 0, so it's not this number. I chose b1 to be different from a sub 1, 1, so it's not this number. It's not this number, it's not this number, it's not this number. This number b does not appear anywhere on my list. Which means that my function from n to 0, 1 missed this number b because it's nowhere on my list, which means that f is not surjective. So hence, b is in 0, 1, but not in the image of f. So f is not surjective. Hence, f is not bijective. So the interval from 0 to 1 is uncountable. Okay, so let me just take a small breather here. This, I think, is really, really cool. It's also like a really elegant idea. Before this lecture, unless you had heard of Cantor diagonalization before, it seemed kind of crazy to think that you could ever have an uncountable set, I think. A set with so many elements, you can't even list them all. But we have a really cool technique here. Suppose that you have a function to 0, 1, right? I'll come up with a number that's not on your list, which means that it's impossible, no matter what your function is, you can't possibly list all the numbers in the interval from 0 to 1. And again, the technique is extremely elegant, but you need to be a little bit technically careful just to make sure that you end up with a decimal and normalized form that isn't 0, which is why I've chosen like 3 and 4. You could choose like 2 and 5. You could choose like 7 and 8. You probably want to avoid 0 and 9 to make sure that you always end up with a normalized decimal in the correct range. Okay. So now we found truly a bigger set than n. So definition, a set A is said to have cardinality C, where my C is my fancy math frac C, if A is equinumerous with 0, 1. We write that the cardinality of A is this fancy C, and we say that A has cardinal number C. Okay. So anything that has the same cardinality as the interval from 0 to 1 has cardinality C. Notice that, by the way, that this proof also shows that R is uncountable, right? Because if you can't list every real number between 0 and 1, you definitely can't list every real number. But it seems like actually R should be much bigger than 0, 1. I think 0, 1 has an incredible number of numbers in it. It's uncountable. But isn't R way bigger? Because R goes from negative infinity to infinity. It has infinitely many intervals. So it seems like R should be way bigger. But it turns out that actually R has the same cardinality. By the way, all these things just show that it's incredibly hard to understand infinity. All of your intuitions suddenly break. Maybe not all of them, but some of them. Okay, and the proof is essentially pre-calculus. So first, 0, 1 is equinumerous with the interval negative pi over 2 to pi over 2. Since the function f, where I will just I'll scale everything by pi, and then I'll subtract pi over 2. Right, so this function sends 0 to negative pi over 2, and it sends 1 to pi over 2, and it does it linearly. So this is a bijection. You can prove by hand that it's injective and surjective if you just graph it. If you just graph it, what it looks like is it looks like this. It's a straight line between this point and this point, and so it's clearly injective and surjective. And now the point is the tangent function from negative pi over 2 comma pi over 2 to r, which sends x to tangent of x is also a bijection. Right? What that function looks like is it goes from negative pi over 2 to pi over 2, and it's an increasing function, so it's injective, and it goes to plus or minus infinity, which means that it's surjective. So this shows that R is the same cardinality. It's equinumerous with the negative pi over 2 to pi over 2. This shows that negative pi over 2 to pi over 2 is equinumerous with 0, 1. So these two are equinumerous, which means that R also has cardinality C. So also kind of amazing, I think. Now, you definitely need to have seen this, I think, as an intro to proof student, just to know that there are different sizes of infinity that behave kind of crazy. And there are tons more questions that one could ask that we don't have time to get into in this class. But let me just try to whet your appetite. So many more questions that you could ask. So for example, are there infinities smaller than Aleph naught? Right? We looked at the natural numbers. That's an infinite set. We found bigger infinite sets in the sense that you can't put them in bijection with n. Right? So I should say that what do we mean by smaller or bigger when you're talking about infinite sets? The point is that you can use injections and surjections to get some handle on the different sizes of infinity, right? So there exists an injection from n to r, but there does not exist a surjection from n to r because they're not in bijection, right? So this sort of says that r is bigger than n because there's an injection, but there's not a surjection. So I could ask, does there exist an infinite set A such that there exists an injection from A to n, but there does not exist a surjection or a bijection from A to n? I think this is a good question. Can I find a smaller infinite set that's still infinite? And it turns out the answer to this question is no. So in some, what that means is that the natural numbers are like the smallest infinite set. The smallest infinity is Aleph naught. Of course, there are, right? I mean, I could take like the even natural numbers, but those are still in bijection with n. So they're not like a smaller cardinality. They're just a subset of n. Okay. I think maybe this first answer is believable. So like if you just try to build a very small infinite set, the one you get is probably going to be the natural numbers, I think. Second question is, are there cardinal numbers between Aleph naught and C? In other words, are there any infinities in between the natural numbers and the real numbers? Because somehow the real numbers seem way, way bigger than the natural numbers. You could ask, well, are there any intermediate sizes of infinities? Okay, this question is called the continuum hypothesis. And you should Wikipedia this, you should Google it, you should watch some YouTube videos or something, because amazingly, it's been shown that the continuum hypothesis is independent of the axioms of modern set theory. In other words, using modern set theory, we've shown that you cannot prove it to be true or false using modern set theory. So this is kind of a crazy answer. You need to take maybe a mathematical logic course to really understand what I mean, but this is independent of modern set theory. as in it's proven that you cannot prove whether it's true or false. So the answer to the question is maybe, maybe not. You could probably ask some math professors, some CS professors, do you believe in the continuum hypothesis or not? They'll tell you probably. So the answer is maybe, but it doesn't affect your life in some sense because you can't prove it true, you can't prove it false. That's one of the most surprising results in mathematics, I think. So you should definitely look into this more. It's really crazy. It's hard to think about even. Okay, what's another question about infinite sets? Are there bigger infinities? Are there cardinal numbers bigger than C? Again, in the sense that there might be an injection from R to the set, but no surjection from R to the set. And the answer to this question, right? It seems like R is humongous. The answer to this question is actually yes. But it's not like the complex numbers. It's not even like the plane. I should say like R is equinumerous with C. It's also equinumerous with R cross R. So this is like the plane, this is like the number line. Those are actually equinumerous. I think that's also kind of a surprising fact. But one example is given by the following theorem, which is called Cantors Theorem. Also an incredibly clever theorem. Cantor has some really, really beautiful, clever arguments. Here's the theorem. For any set A is not equinumerous with its power set. And so if you take the power set of R, it won't be equinumerous with R, it'll be bigger than R, right? Because the power set is a set of all subsets. So the example here with yes is you can take the power set of R by Cantor's theorem. It's not equinumerous with R. And we can even prove Cantor's theorem. Again, it has a beautiful proof. Okay, so suppose for contradiction that A is a set such that A is equinumerous with its own power set. That means that there exists a bijection. Then there exists a bijection F from A to the power set of A. That's by definition of being equinumerous. So just as an example, if we took A to be n, then we would be able to write down a bijection from n to the power set of n. So you might have something like, so f of 0 should be an element of the power set, maybe the set 0, 2, 8. Maybe this will take the set 1, 3. F of 2 will take the set 0, 1. Maybe f of 3 is the empty set. That's an element of the power set. Maybe f of 4 is the set of even natural numbers. Maybe f of 5 is all of n. I'm just trying to get you to picture what a bijection between n and the power set of n might look like. So we have, by assumption, a bijection from A to the power set of A. So notice that sometimes A is in, so if you take in sometimes for element A and A is in f of A, and sometimes A is not in f of A. What do I mean by that? Well, go back to this blue example. So in this example, 0 is in f of 0, right? Because f of 0 is an element of the power set of n. It's a subset of n. Sometimes 0 is in that one. 1 is in f of 1. But 2 is not in f of 2. And 3 is not in f of 3. but 4 is in f of 4, and 5 is in f of 5. So sometimes a will be in f of a, and sometimes a might not be in f of a. So now comes the very clever idea. Define a set S to be all of the a's in A such that A is not in f of A. Again, sometimes for little a, it will be in f of A. Sometimes it won't be in little f of A. Let's just take all the a's such that A is not in f of A. Right, so in this example, if we go back to this example, S will consist of 0 is not in there, 1's not in there, 2 and 3 are in there, and then some other numbers are in there, potentially. This is a very clever set because of the following reason. So F, I'm assuming, is bijective, and S is a subset of A. Right? S consists of some elements of A and and maybe it leaves out some elements of A, but it's definitely a subset of A. So S is in the power set of A. It's a subset of A. Now, since F is surjective, that means somewhere in this list, S has to appear. So since F is surjective, there exists an X in A such that F of X equals S. Now, I'm going to ask the question, is X in S or is X not in S? So either X is in S or X is not in S. Only two possibilities. Right. So I'm going to make a longer slide here than normal because I think I want to be able to scroll up to look at the definition of S. So case 1, if X is in S, what does that mean? To say that X is in S means that X is not in f of X. Then X is not in f of X by the definition of S. But f of X is S. So this says that X is in S and X is not in S, which is a contradiction. Okay, well, what about the other case? If X is not in S, again, by the definition of S, that means that X is in f of X. By the definition of S. But again, f of X is S, so X is in S, but then X is in S and X is not in S. This is also a contradiction. So no matter the case, we've arrived at a contradiction, which must mean what we assumed is false, which means that A is not equinumerous with the power set of A. So in any case, we arrive at a contradiction. So what we assumed must have been false. A is not equinumerous with the power set of A. The power set of A is basically always bigger. So if you take the power set of R, you'll get a bigger infinite set. If you take the power set of R, you'll get an even bigger one. In other words, you can get as many infinities as you want. Bigger and bigger ones. Okay, so just as a corollary of this theorem, sort of immediate, the power set of n is uncountable. Right, because the power set of n is definitely going to be infinite. you can easily write down an infinite number of sets inside of the power set of n, but it's not equinumerous with n by the previous result, which means that it's uncountable. Okay, so it turns out, actually, we're not going to prove it. We don't have enough tools, actually, that this is actually equinumerous with R. So this is just somehow like, I mean, this is an infinity we already know about. But we can't prove it yet. Okay, so hopefully you found this kind of interesting. I really think it's very interesting, and these two Cantor proofs are just like somehow very, very clever. And thinking about infinity can kind of make your brain hurt. But hopefully you found this kind of interesting. Yep. I think that's plenty for today. So see you next time.